to add or subtract from the topic, edit it, and when you write down the introduction, which is due next week, just 2 page, just 2 page introduction, background, what other uh, state of the art people, what have they done in the, and how are you going to contribute in this paper. My main objective is when I will guide you, I will mentor you slowly, but my main objective that the paper should get some at least national recognition in the peer reviewed either conference or journal paper. The more you publish is better to, although you will still get credit from the classroom project submission, but I want you to get some recognition outside the classroom that will help you to um, improve your research expertise. Okay, so by the way, were you were you able to, are you satisfied, at least the people who are in the classroom, are you satisfied what I just selected approval, or you still have some other options to share with me? You good?
Yeah.
One group says they are good. You good? Okay, that's good. On the online students, can you open your mic to share with your professor that are you good on the project's approval, which I just did today?
Yes, sir.
Yep, I got mine too.
Maybe they are still working. Oh, my speakers were muted. Can you tell me if you open your mic? You guys are good.
Yeah, I'm good with mine. I was able to take a look at it earlier today.
Yep, same here.
Even then, if you still need to edit it this week, we are still, it's very rough. Like, I like your topics. Uh, you have some like knowledge and resonance, people who are trying to find some related topics with their vibrations so they can do work. So it's a, I will be your like a co-author, so you can finish your paper and I will review it as a last co-author. Usually professors are at the end of the, names are at the end of the, so I will try to get it published. That's my objective. That, you know what happened last year, students were able to publish their papers with a little bit efforts required, but I'm not pushing you guys. You still have quite a lot of time for preparing for your uh, project. Okay, let us begin our lecture. Lecture 4. By the way, I will be able to finish grading by this week, and you will have another quiz this Sunday, which will cover, or maybe I should give you some more time. What do you suggest you need? Because you just submitted the paper abstract. Maybe I think the in-class students say they need more time for the quiz of chapter 3. Do you, how about the online students? Do you need more time, or are you prepared for the chapter 3 quiz this Sunday?
I wouldn't mind a little bit more time.
Okay, let's do it by the next Sunday. We will finish next Sunday. I will assign you maybe one quiz. Then following Sunday we will have a test from whatever we study from chapter 1, chapter 3. Okay. So please note this down. Can you see my screen?
Yes, sir.
Okay. Our next homework assignment is related with the Rayleigh energy method. How to derive the equation of motion using the Rayleigh energy method. So this is the equation which you will be using for finding the energy method, where Tm is the maximum kinetic energy, which is half m v square, and v max, it depends upon the two things. V due to the gravity, it's V stands for, by the way, V stands for potential energy, and potential energy is split up into two parts. I would say due to the gravity, like for example, this is floor, and you want to bring the mass up on this height, up like over here. So the mass has acquired a new position too from one, so it has gained some height. So when it gains some height, the potential energy to the gravity, it increases. So that's the one part. Another part in the potential energy is due to the spring. So if you have a spring and you compress the spring or stretch the spring, so for example, if you stretch the spring by delta x, so this is, suppose this is grounded, so that is the kinetic potential energy stored into the spring. I would say due to the spring, it is half k delta x square. So when you see the potential energy in the Rayleigh equation, Rayleigh energy method says that you should have the energy at any location as a constant. This is equal to sum of the T mean plus T V max. An equilibrium position where x equals to 0, the potential energy is when the displacement is maximum is, so it varies from 1 point to n. For example, let me show you one example. So let me show you one example here. For example, this is my uh, simple pendulum, and it is oscillating at a certain harmonic, and this oscillates back and forth. And I want to apply the energy method, or which is the Rayleigh energy method, to derive the equation of motion. So how am I going to find out this one? So let me show you. So you can apply this equation over there. So to see at each location, this is so for example, this is my datum line. This is my datum line, and this is the height gained from position 1 to position 2. And let's focus on two position 1 and 2. So over here, maximum position, you have maximum potential energy at location 1. How about the at location 1? How about the kinetic energy? It's 0 because it stops there and comes back. That's why you see the minimum kinetic energy at the maximum height, it goes to 0, then it starts oscillating on the other side. It changes its motion uh, from from right to left. It changes its motion. And then comes the other side, which is location 2. In location 2, you have T max. It has maximum kinetic energy, which is given by this formula, and V min. So over here, so you can write it down here, another form, T max equals to V max minus V min. And in this case, V is just the gravity. I was about to tell you about this. So when you see such a question in which there is a spring, so you have to add this spring potential energy as well. But in this case, like in the pendulum, we don't see any spring, so we just rely. So whatever we have T max, is equal to V max in this case. So that's how you're gonna solve this type of question. So let me show you one example. Or before let's do one example here. So mass spring system. This is spring attached with the mass is attached with the spring, and this is the degree of freedom, and it oscillates back and forth. And when you give initial condition, to suppose this is my initial condition, and you just release it, it goes back to over here. I would say this mass goes up and down. This is my mean position. Mean position x is suppose 0. So if you want to just stay at 0, goes positive and goes to negative, goes to positive, negative. It starts oscillating with respect to time, and this is my displacement. So this is how it looks like, a simple harmonic motion, a sine omega t. So if I apply this formula, Rayleigh energy method, to derive for differential equation of motion, how am I going to do that? You look, I will use this formula and then apply it over there. So if I use this T max of m v square, and make sure you understand that delta is the deflection, static deflection. When the mass attaches with the spring deflects statically by a distance we call it as a delta, static deflection. So the V max, I will say V max VGV due to the spring, and V max, I can write it down here, half Kx max plus delta square. Because the spring can the potential energy stored in the spring can be written as half Kx square. Potential energy stored in the spring is equal to half K delta X square. So I'm assuming that before the mass was attached, it was, you have to add the static deflection into that total displacement or the total stretch of the spring, and that way you will account. But you know that the spring static deflection, you know the spring, when it statically deflects, the spring force equals to K times X or K times delta if it is statically deflected. That is equal to the weight of the mass, sorry, the weight of the block which is attached with this spring, that is statically balanced. So if I want to find out the V max, so I can write down V max, this is max minus mg. By the way, why am I write down minus mg x max? Because negative sign shows me that it goes down. When it goes down, you are losing potential energy from the datum line. Suppose this is my equilibrium is my datum line. Okay, guys, this is my datum line, and I want to add this gravity term, which is mgh or mgx minus. This is my, suppose this is my x max displacement. Agreed. So you have to subtract that because it is going down the datum line. It is going below the datum line. That's why I have to subtract that from the for the v gravity. And what is v minimum? This is half k. What is the spring deflection? K delta square. So what's that? So I'm going to equate it. I'm going to equate it over here and then see T max, this equation. T max equals to V max minus V min. So let's equate it. So I'm gonna write down half K X max. Let's say it is M stands for max. Okay. Delta square minus mg X max minus half K delta square. And the left hand side is what? Half K, sorry, half M V square. Half M V square. And we know that this is also correct. Static deflection is balanced by the weight of the block. So if we do the math here, so half K X max square plus delta square plus 2 times X max times delta minus mg X max minus K half K delta square. So if we take a look here, so this is cancelled by, let me open this so that you should having no confusion, plus half K delta square plus K X. This is cancelled by this one. What is this? Look, we already know that K delta equals to mg. Can I write down K delta as mg x m? I'm just replacing K delta by mg. Okay. So can I cancel these two terms together? So this is cancelled because the K delta we already know it is statically deflected due to the mass attached with the spring. So that's why we can cancel them easily. So we are left only this term. On the left hand side is half mx dot square. On the right hand side, this is half k x. This is m, maximum velocity. So now what is x dot? Let's plug it in. Let's do after this. This is cancelled by this one. So what is the x? What is maximum displacement according to our simple harmonic motion? I can write down the displacement of the mass in terms of sine wave or cosine waves. So let's write it down in terms of sine wave. I can write it down like x equal to a sine omega t. What is my x maximum amplitude is equal to a. Agreed? This is my amplitude, which is the a. So I'm sorry, this is a little bit up, but this is a. So that's the maximum amplitude. And I'm gonna write down in place of x dot m. What is the maximum amplitude of the velocity? So what you have to do here, look, I can take the time derivative of this equation. And you guys can tell me what is the maximum amplitude of the velocity. You whatever the coefficient of the cosine wave, that is the maximum amplitude. And one more thing, look, one more thing here. This can be written as sine wave, and sine and cosine are related with this term, like sine omega t plus pi by 2, that is equal to cosine omega t. So I can write down this as a x over here. Let me rewrite here. I'm sorry. This is x equal to a sine omega t, or x equal to a cosine omega t with the phase shift of pi by 2. So I can rewrite here x dot equals to omega x. This is omega. Sorry, this is omega times x. And now if I do one more thing, look, I want to take another time derivative. Okay, let's wait one thing. I want to show you one thing here. What I wrote down here, I can rewrite this equation as m x dot square equals to k x square. Can I replace x dot square by omega x? Can I replace that? If suppose this is m maximum. So can I replace this omega x? Can I write down like this? This is m. So, and then I can just simplify this expression. X square, this is omega square, x square half, sorry, x m square. So m. So I can just cancel this out. So what I'm left with, omega square equals to k over m, or square root on both sides to find out the natural frequency formula. This is the natural frequency formula of the object which is oscillating with a simple harmonic motion. That is a very important formula for your finding the natural frequency. For finding the natural frequency, you should learn it by heart. Let's do one problem. Apply the Rayleigh method of energy. I would say Rayleigh's energy method. And what's that? That is saying T max equals to V max minus V min, where V stands for potential energy due to the gravity as well as due to the spring. And then T max stands for the maximum kinetic energy. Now, guys, let's do this equation. So I want you to understand one thing. So this is, suppose this is pendulum here. Okay, this is my datum line. Okay, this is my datum line, and you will help your professor with one thing. So I want to show you, whenever you see masses, there is just one mass. Whenever you see masses, if there are two masses, three masses, whenever you see them, you will always say they possess the kinetic energy. So T max half m v square. Uh, I'm I'm gonna show you maximum value is not a big deal. Like if maximum value of the velocity is a times omega, okay, in our simple harmonic motion. So I'll come back to this one. So have you understood why have I written down half mv square? Okay. Now you will tell me one thing, that what is x equals to. So can I write down x as, okay, can I write down x as L theta? It's just like arc length. This is the like theta is very, very small. Assuming theta is very, very small. So if it is very, very small, although this is zoom in, so I can write down x equal to arc length, which is L theta. And what is x dot equals to? L theta dot. Okay. And if I plug in x dot square, you will help your professor. You will say, Professor, this is L square theta. So I can write down here a half m L square theta dot square according to my understanding, with the arc length, everything. By the theta has been taken very, very small. And you will also help me. What is this perpendicular height from the datum line? Look, this is a triangle, right angle. Look at this. This is a right angle triangle. Okay. And what is this side of the right angle triangle? You will say, Professor, this is L cosine theta. And what is this whole length? You will say, this is L. So what is L minus? So H equals to L minus L cosine theta. Agreed? So that's the difference in these two lengths. That difference give you the height gained in moving the simple pendulum to the extreme end. That's the maximum height gain. So potential energy is due to the gravity, can be written like mgl 1 minus cosine theta. And you know that cosine theta, for theta equal to very, very small, approximate to zero, I would say a very, very small angle. So I can write down cosine theta in this form, and sine theta in this form. So I can rewrite this potential energy, rewrite the potential energy mgl with a linearized model. So after we do the higher order terms are neglected in the cosine theta, I can rewrite 1 minus theta square by 2. And then you open the parentheses here, mgl 1 minus 1 plus theta square by 2. So that is my potential energy. And for the maximum potential energy, we get mg L theta square by 2. Now here comes the question. What is maximum angle? You remember I gave you this formula earlier, that the any sine harmonics any simple harmonic motion can be written in terms of sine and cosine waves. So, but here in this case, this is not x. I would say this is theta. So I can write down theta as a sine omega t. So what is my maximum theta? You will tell me, Professor, this is equal to A. Agreed? The amplitude is the maximum value of the variable, whether it's theta, theta dot, theta dot. How about the next? Look over here. We want to find out what is maximum theta dot velocity, maximum theta dot. Before for that, we need to find out the time derivative of this equation, which is a omega cosine omega t. And what is theta dot maximum? The amplitude of this signal. You will tell me, Professor, this is a omega. That is the maximum amplitude of the velocity. So let's plug it in the Rayleigh energy method. So I'm gonna use this energy method and plug it in over here. By the way, V min is located at this position. It is passing through the datum. So V min equals to 0 in our case. So I can write down the whole equation T max equals to V max half M L square theta dot that is equal to MGL half MG, I would say half MGL, and then in place of theta dot M I can write down A omega. Agreed? And in place of theta M I can write down A square. After this you can just cancel some variable. Look, M is cancelled both sides, A square is cancelled both sides, half is cancelled both sides, L is cancelled by this L. So you're left with omega square equals to G over L. And then take the square root on both sides. This cancelled by this one. So omega equals square root G over L. So this is my natural frequency formula for a simple pendulum. Do you understand how did I find out the equation of motion of simple pendulum using the Rayleigh energy method? You will be solving such problems in the next homework which I'm going to open today, and it will be due like in a few days, maybe 5 6 days, and that way we will finish chapter 3 homework, and there will be uh, a quiz or maybe a test. I think I should, since we have, because more accumulation will be difficult for you guys. So let's do the test the following week rather than the quiz. Does it sound good to you guys, online students? So rather than giving you a quiz from chapter 3 the following week, I just give you the test from chapter 1 and chapter 3. The previous 3 homeworks, just no more than that. Although I might give you some video links, but I'm not gonna assess you for chapter 4, which I'm gonna start after this chapter 3. In class student says yes, is this is okay. How about online students? Is this okay with you guys? The test rather than the quiz?
That's fine with me.
Online students say that's fine with them. So I'm gonna announce this that chapter 1 and chapter 3 there will be a test the following Sunday, not this Sunday, but you still have about 12 days, which is sufficient. I think if I were you at your place, I would say this is sufficient. Oh my god, I'm gonna break it. Okay, let's do one more problem. Okay, let's apply the equation of Rayleigh energy method. So I would say T max, potential energy max, potential energy min. So our this center is moving at a displacement of like this is my degree of freedom, which is like written like this. This book tells us this is grounded in the air, but it is just the position uh, of the center of this drum. Determine the natural frequency of the cylinder, which is moving horizontally downward as well as it is rotating. So it has 2 degrees of freedom, x and theta, which are also known as the generalized coordinate. So if I want to apply the potential, the kinetic energy, so you will see this is like a block, like a this is like a block of mass which is also moving, as well as it is performing it is performing a rotational motion as it moves past. You see it is moving and going down. So you have to include 2 types of kinetic energies. One is due to the uh, straight line motion, which is this one, and the second one is the angular motion, which is half I omega square. That was a important point. Have you guys understood that important point? That why have I included 2 types of kinetic energies for this cylinder motion? Because it is translating going forward like this, like this is going forward, plus it is also rolling. It is rolling and performing the angular motion. So it's a combination of 2 types of motions. One is due to the rotation of the drum, one is due to the uh, covering the straight line distance. Are you with me? Understood this concept? Why am I adding 2 different formula? So let's do this. So x equals to what? X equal to r theta. So in this drum, it's like a circle. Okay. So this is linked with this. So this is my r. So let me redraw this for your help. This is my drum. So if it arc length would be equal to x equal to r theta, and the velocity would be equal to r theta dot, and that is a formula T max equals to V max minus V min. And what is the potential energy? So half K x plus delta due to the deflection and minus mg h. So gravitational potential energy be 0 at the rest position. So I want to show you mg sine theta, or mg sine K times delta. So if you closely look, this is my weight acting downward, mg, and this is my motion, straight line motion. So this, when the spring is attached over here, it pulls back. So K delta, it is equal to this stretch when it moves like a straight line. It moves straight. It moves straight line this much long. So what is this equal? If suppose this is phi, in our book it says it's phi. Suppose that this is a phi, and then what is that equal to mg? This is my mg. Okay, this is my mg. This is my equal m. This component is mg sine phi. So I can write down here this potential function as half k x square plus delta square plus 2 times x times delta minus mg h mg sine. What is h equals to? H equals to, from the bottom, from the datum line. This is my datum line. So I will say, let's keep this datum line. Or this one is datum line. And if it comes over here, so what is this height equals to? This height, or this height equals to h equals to x sine phi. You should be able to do this. Is h equals to x sine phi. So I can write down mg sine x sine c. This is in place of h. And when you solve for this half k, let's open the parentheses here. Half k x square plus half k delta square plus x times delta minus mg x mg x sine phi. What is that mg x sine phi? We already know that mg sine phi equals to k delta. So can I write down? Can I write down like this? Mg or kx k delta. And what is our v min? So before I do the v min, I want to show you that that is equal to half kx square plus half k delta square. I forgot to write down k over here because this k is outside. I forgot to write it down. So this is cancelled by this. So you're left with these two terms only. This is my v max. And v min, when this is hooked up, The spring is attached with a block of mass. It deflects. It deflects a little bit to this. Is my, but this is my V min before it deflects. Or sorry, this is after the deflection. So this is my delta. In the stretch is delta. So I can write down half k delta square. So T max so T max is combination of two energies. Did I write it down already? Half mx dot square. Omega can be written like theta dot square. I can rewrite this in terms of one variable x equal to r theta, x dot equals to r theta dot, and theta dot can be written in terms of x variable x dot over r. So I'm gonna write this down as half I x dot square over r square. This is about the T max. Half is outside the parentheses and x dot square is outside the parentheses m plus I over r square. So that is my T max. Now I'm going to do the explanation of this. This for T max, what is my x? So we know that x equals to a sine omega t, and x dot equals to a omega. This is the natural frequency, by the way. So the maximum amplitude, this is my maximum, that is equal to the coefficient of sine or cosine signal. So I'm gonna write down this one again. Half a n whole square m plus I over r square. And I'm gonna write this down. V max, and then I'm gonna write this down, V min. So let's combine them together into one equation, which is the Rayleigh's equation. I can write down this side half a square omega n square half k x square, and I can replace x by a square. So I don't need to write. A is the maximum amplitude. This is my max. This is my max. Sorry, this is not the max. Half k delta square minus half k minimum k delta square. This is cancelled by this one. So what is a square is cancelled by a square, half is cancelled by this half. So omega n square equals to k over this is your answer. So when you go home, redo this problem. And this will help you to solve some of the homework problems at the end of the chapter, which I'm gonna open today. The next topic is free vibration with the damper. What is the damper? Damper is the element, ideal element in mechanical components that resembles a friction force present inside. So for example, this is my equation. This is my schematic diagram. It's a sketch of mass spring and the viscous friction between the contact surface. This is my contact surface, and you see the damper. Our book says damper is by letter C. Some books say this is B, some books say this is C, but you know the force due to the damper is C times velocity. This is the force and this is the velocity. It is directly proportional to the velocity. The larger the velocity, the larger the force. And if I do the equation of the free body diagram, this is the mass and this is the displacement, and this is the force acting on the mass, and this is a damper. So the damper is here, negative Cx dot. And another force which is opposing the forward motion is Kx. So I'm going to write down negative sign because both are opposing. So I'm going to apply the force, Newton's second law, F minus Cx dot minus Kx equals to Mx double dot. And I can rearrange the highest order first and the descending order terms. Okay, guys. Now let us say the solution lies as a simple harmonic motion. It can also be written e to the st. What is Euler formula? St means like cosine st plus j sine st. This is like combination of sine and cosine wave. That's why I replace x by, I can write down the displacement of this mass back and forth as a simple harmonic motion, which is a combination of sinusoidal signals. So I can find out x dot and x double dot and plug it in over here in this equation. I will plug in x dot from here. What is the derivative of this? As e to the st. What is the derivative of, again, take another derivative, as square e to the st. And then I can replace this in this equation. I can rewrite this equation by plugging in these variables. So m a s squared e to the st plus c a s e to the st plus k a e to the st. Agreed? So equals to f. So a e to the st is like an amplitude. Simple. This represents the back and forth motion, and this cannot be zero. But the other factor can be equal to zero, and that will give me some information. For example, this my right hand side is zero. For instance, you give initial conditions. So a e to the st cannot be zero because it is not at rest. It is moving. And the other factor, this factor can be zero. Ms square plus cs plus k can be zero. So that will give me the quadratic formula. We know all of us, we know that quadratic formula can be applied to a quadratic equation, minus c plus minus c square minus 4mk. And this is our equation in our book. Let me show you this equation. Yes. And the discriminant will tell you the types of roots. Like, as there are two roots, it could be real, and it could be repetitive, and it could be imaginary. When the discriminant is positive, you will see real roots. And when it, in that case, this is the overdamped system. And if the two roots are in terms of like complex conjugate, we call this is the what we call overdamped system. Over the roots will define the system response. Overdamped response, when you see the roots are complex conjugates to each other, this is underdamped system. And when you see the discriminant is 0, then it's a repetitive root, so minus c over 2m, repeating root, so it will be lying somewhere minus c over 2m, another root lying on the same. This is not a critically damped system when zeta equals to damping coefficient equals to c. Critically damped system, c, sorry, this is equal to 1. In that zeta, what is zeta? You are studied in the undergraduate school. That zeta is the damping ratio. And if that is equal to actual damping divided by the critical damping, actual damping divided by 2m omega n, or can also be written as 2km. This is equal to zeta. And let me show you the response. I'm about to show you another important section. How are you going to define the response for the positive roots? The response looks like very sluggish. Zeta is very, very large. And for the repetitive roots, suppose this is repetitive roots, it will come back slowly to the, but not that slowly, but it's the critical time. So this is my case 1, this is my case 2. Case 1 is sluggish response, case 2 is a little bit faster response. How about the imaginary? This is my imaginary axis, this is my real axis. How about the imaginary r plus iq and r minus iq? This is q is like imaginary part of the component, so this is my q. Okay, this is my q, positive q, this is my negative q. But anyway, this is not important. The important thing is that response looks like you give initial condition, the system will come back, the mass will come back and oscillates and then comes to rest. So this is known as the, and this is on the left hand side of the complex plane. We usually call this as a Laplace plane or the complex plane. And as long as the roots are on the left hand side, the system is stable. But as soon as it goes to the right hand side, suppose a root is lying over here, look, the system response will grow exponentially, and the envelope it keeps on. So the system becomes unstable because it will exponentially keeps on growing, the amplitude keeps on growing. Let me show you an example of the unstable pendulum. This is unstable pendulum. Why? Because if you give initial condition to this location, will it come back to, it's a inverted pendulum, will it come back to its mean position? No, it will fall down, and then it will lose, it will not come back to mean position, so it will grow exponentially, and this will be so the thing is, we can find out some equations. There are certain equations, I don't want to go into the theory, but I want to show you a table which you need for your test. That table I'm going to copy and paste. You need it for your test. I was talking about the three cases. Distinct real roots are overdamped system, and this is the displacement formula where A is this, A1 is this one, A2 is this one. You don't have to derive it. I will not ask you to derive the equations of these displacements. I will just give you some problem and you will have to identify which case is this. And once you identify the case, then you can plug in the equation to find out the response of the system. And the repeated root critically damped system, both are same roots. Then this is the formula. This is the formula for the same roots. What is A1 initial condition, A2 V naught minus R1 X naught. And in the third case, complex roots under damped system, the response is so this is the formula. X equals to B e to the RT real part sine QT plus phi. Q is the component of the what we call the imaginary component. Let's do one problem and then you will understand more clearly how can we apply this formula in our case. So let's do one problem together. Open your notebooks. This is obtain the free response of the following function. A initial condition x of 0. So 2x double dot plus 10x dot plus 8x. So let's do A. Ax equal x of 0, initial condition of the displacement is 2, initial condition of the velocity equals to 5. Let's focus on this one. So, and then you can compare mx double mass, damper, stiffness. So I can compare this equation by this equation. So what is mass? Mass equals to 2. The coefficient of the second order is the mass. Coefficient of the first order is the damper. The coefficient of the 0th order is the spring stiffness. That's how you will pick it up. And if you do the math, can you find out in MATLAB? Use MATLAB, but you are not going to use in your exams. You will use some from roots. This is the descending order of the equation. 2. I would say, why am I writing down? This is not a quadratic form, but you know I change this into quadratic form. I can write down this ms square plus cs plus k. Agreed? I did that earlier, so I don't want to go this into the detail. And then if you find the roots, can you help your professor? What are the roots of this equation? So if you open your MATLAB, the roots are, by the way, this is very easy to find the roots here. So roots are x equals to -1. This is the first root, second root equals to -4. Do you get the same answer, guys? In class, they say yes. Online, do you see the same answer? Online students also say yes. So let me write it down here. My MATLAB is uploading. Can you see my MATLAB? Maybe okay. So you plug in two roots is the equation, the function 2, 8, 10. Sorry, 2, 10, 8. You see the answer. So let me copy paste what I wrote down here in MATLAB. I wrote down this roots to the formula. Make sure you write down in the descending order of the polynomial highest degree first. So I wrote down as the coefficient of the highest degree first and the second degree, which is 1. So in that way, you will be not losing any sequence. So for that, if there are two real roots, I'm going to use this equation to find out the response. So what's that? So that is equal to, look, I'm going to use x of t, time domain, x of t, a1 e to the negative t, a2 e to the negative 4t. And then a1 can be found. What is a1? Let me show you. A1 equals to v naught. Let me write down here. A1 equals to v naught minus r2 x naught, r1 minus r2. Let's plug it in over here. Let's find out what is my a1. And then let's plug in what is v0. V0 means velocity at 0 time, which is 5. So can I plug in 5 here? Let's plug in 5 minus root 2 is minus 4 times x naught. X naught equals to 2. Agreed? Divided by r root 1 minus root 2. So can you solve for this? 5 plus 8. 13 over 3. Agreed? How about the a2? So let me find out the second constant, which is a2. It is written like a2 equals to x naught minus a1. So let me plug it in over here. X naught minus x naught equals to 2. 2 minus 13 by 3. And if you do the math, you can just you can do the common denominator here. 6 over 3 minus 13 over 3 minus 7 over 3. I got minus 7 over 3. Do you get the same answer, guys? So let's write down the whole equation as one equation. I'm going to plug in everything here. So for you, so if you understood this question, I think you should be able to solve the remaining question by yourself at home, because you are a it's just the equations. You have to plug it in equally. So 13 over 3 minus 7 over 3. That is the displacement. If you make a vector in MATLAB for time, so you can plug in. Let me show you very quickly. I'm going to make a vector for time. Time equals to, for example, it goes from 0 and 0.01. And let's go for 10 seconds long data. So I'm going to plug in x equals to a1, which is 13 over 3, right? 13 over 3, 13 over 3 times t, e to the negative t, times e to the negative t. And plus it is, sorry, negative sign, negative 7 over 3 times e to the negative 4 times t. So let's plot it. Plot time versus x. So that's how you plot. So I'm going to show you. And it looks like a real root. It's not a oscillating. So this is the formula. I just plug it in. Let me show you the response. In our MATLAB, the response is, it looks like, I'm sorry, this is not a response. So you see, it's not oscillating response. So it means it is not underdamped. This is the uh, overdamped system. All right, with that, I'm gonna end this lecture. Thank you for coming to the lecture. So I'll see you next week. Where is my lecture? Here it is. Stop recording.